Hello everyone, welcome to Digital Communication Tutorials. In this video, I'm going to derive an expression for the signal to quantization noise ratio for a Midriser quantizer. To start with, let us consider the quantizer input x represent the sample value of some random variable capital X with mean 0 and variance sigma x square. Now let us assume the quantizer to be uniform, symmetric and Midriser type. Let x max represent the absolute value of the overload level of the quantizer input and delta denote its step size. We may now express the number of representation levels in the Midriser quantizer as capital L equals 2x max divided by delta, where x max, as we already have said, is the absolute value of the overload level of the quantizer and delta is its step size. This is one way of representing the number of representation levels in the quantizer. Further, we know that for a binary code word of n bits, we can have up to 2 to the power of n representation levels. Since we have considered here a Midriser quantizer and the number of representation levels for a Midriser quantizer are even, we can once again write an expression for the number of representation levels as capital L equals 2 power n. So, we have now expressed the number of representation levels of a Midriser quantizer in two different terms. So, let us now equate them and try to solve for delta. Now, I am taking the RHS of equation 1 as well as that of equation 2. I am going to equate them and solve for delta. So, 2 into x max divided by delta equals to 2 power n. Upon rewriting, I get an expression for delta as 2 into x max divided by 2 power n. Continuing, we will now write an expression for the signal to quantization noise ratio, which is given as SNR output equals sigma x square divided by sigma q square, which is equals to sigma x square divided by delta square divided by 12. This derivation was done in one of my previous videos, that is by the topic quantization noise and signal to noise ratio. I would like to request you to kindly refer to that video for more information on this derivation. Further, we know that the signal power, which is represented by sigma x square, is proportional to the square of the input signal x of t. That is, sigma x square is equals to x square of t. Now let us assume that x of t is sinusoidal. Then the signal power is written as sigma x square equals x max square divided by 2. So we will now substitute for sigma x square as well as delta into equation 4 and simplify, which is given here. So SNR output equals sigma x square divided by delta square by 12. Sigma x square, as we know from equation 6, is x max square divided by 2. We will place it here first. Then we are going to take the value of delta and write it here. So we have the square for the delta as well. It should be noted. Let us now simplify this part. I will take 12 to the numerator first. So it will be 12 into, we have x max square divided by 2 in the numerator, divided by, in the denominator we have 4x max square divided by 2 to the power of 2n, which is what is written here. Let us first cancel x max square and therefore we will have a new equation given by 12 into, the denominator term here comes to the numerator. So it is 2 to the power of 2n divided by 4 multiplied by 2. Upon simplifying, we will get it as 12 divided by 8 into 2 to the power of 2n, which equates to 3 divided by 2 into 2 to the power of 2n. This is the expression for the output signal to noise ratio of a Midriser quantizer. However, we should note that we commonly express the signal to noise ratio in terms of decibels. So let us now apply 10 log 10 on both the LHS as well as the RHS of equation 7, which is given here. So 10 log 10 of SNR output equals 10 log 10 of 3 by 2 plus 10 log 10 of 2 to the power of 2n. Now 10 log 10 of 3 by 2 is equal to 1.7 plus we have 2n term here. When I take it here, it will be 20n. Then we have log 2 to the base 10, which is 0.3. So this simplifies to 6n. So the final expression for the output signal to noise ratio of a Midriser quantizer is given by 6n plus 1.76. From equation 8, we note that Each bit of the code word of the PCM system contributes 6 dB to the signal to noise ratio. This is also commonly called as the 6 dB rule. Right. So that is about the discussion on the signal to quantization noise ratio for a mid-riser quantizer. If you like this video, kindly press that like button and subscribe to my channel for more videos on digital communication. Thank you for watching. Have a good day.